Pneumatics, and we are here to present to you our project, the Pneumatic Pass-Thru Impact Wrench. My name is Felipe, this is Ryan, and Milton. First, I'd like to explain the concept of our project. We are combining three existing tools, the pneumatic ratchet, the impact wrench, and pass-through sockets. The main goal of our project is to make this tool small, powerful, and ergonomic, as well as have it meet or exceed industry-standard performance. The first technology is the pneumatic wrench. It is a common mechanical tool used to tighten and loosen small to medium-sized fasteners. The common socket drives that you'll see used by this tool are 1/4, 3/8, and 1/2 inch. This tool is also equipped with 40 to 50 foot-pounds of torque, rotational speed of 150 RPMs, and it consumes air at a rate of 3 to 5 cubic feet per minute at your standard 90 PSI. Second technology is the impact wrench. Similar tool, except it's much more powerful. It is used to tighten and loosen medium to large size fasteners. Common fasteners you'll see used by this tool are 1/2, 3/8, and up to 1 inch socket drive. It is equipped with 75 to 2,000 foot-pounds of torque, 5 to 10,000 RPMs, and consumes air at a rate of 4 to 6 cubic feet per minute with 90 PSI. Finally, the pass-through sockets. This is a relatively new technology, emerging technology. It enables long studs and rods to pass through the ratchet as well as the socket, which means that it eliminates the need for deep sockets, and it has a low profile. To summarize our design goals that were just mentioned, we want it to be easy to use and ergonomic. We want to increase the torque, increase the RPMs, and reduce the power consumption. The impact mechanism that our tool is equipped with will result in anti-lashback, which increases the safety for the user, and it's compatible with existing pass-through sockets. As you can see here, we have a layout of the internal components of the original pneumatic ratchet that we based our tool from, separated into 3 sections. Here you have the handle, the turbine with the impact mechanism components, and finally the head. The head is the part that we manufactured and modified. So this right here is a quick schematic of the pin and clutch mechanism. Once they all come together, they form the reactionless impact mechanism. There's a close-up of the headpiece. So what we did is that we reconfigured it completely. We machined it from scratch. We designed the pawl, the hub, and the yoke, as well as most of the head. This is a conceptual design that we came up with during the beginning stages of our project. As you can see, the arrows are pointing at the impact mechanism, which is relatively in that area internally, as well as the unique pass-through head design. So the benefits of our project: it's environmentally friendly by reducing power consumption, which is a direct result from the increased torque and time. RPM, and that also results in a time saved for the user because it takes less time to remove a stud or a bolt. Like I mentioned also, the impact mechanism is going to increase the user safety of the tool. More about the safety. Common injuries that you'll see in the workplace using similar tools to this are smashed knuckles, cuts, and bruises. With the reactionless mechanism, it isolates the final output drive from the turbine, so it's only rotating when they engage, and the momentum is what causes it to rotate. Also, pneumatic tools have no risk of electric shock. This is a quick overview of the standards that we use for our tools, such as for the materials. We chose S7 tool steel because it's the go-to steel for shock resistance. It's also cost-effective. And we also have the standards for the bushing, retaining ring, and the pawl spring. This is a continuation of the standards. We have to heat treat our part in order to make it harder. These are the different phases of the heat treatment that I have to go through for that, and also the code of ethics that all engineers should use at all times. So a quick little perspective. This 4 to 6 cubic feet per minute at 90 PSI, the air consumption is pretty much a fixed rate. That's what our tool will use as well. However, it's going to use less over time because it takes less time to remove the bolt. To give you a quick real-world example, a Boeing 737 airplane requires about 367,000 fasteners to assemble the plane. In man hours at your standard 150 RPMs, it'll take roughly just over 1,000 hours. our tool is going to reduce that time drastically to around 380 hours at our 400 RPMs. This is a pie chart of, we chose an example, Ingersoll Rand. There's a high demand for pneumatic tools around the world. This company distributes to many different continents such as North America, Europe, Asia, and Latin America. Compressed air is universal. It's hard to see, but these, the photo in the back shows adapters that can be switched in order to fit into any compressed air system all around the world. There's an overview and a breakdown of the costs associated with our project, such as the design, prototype, manufacturing, and the total hours spent. The total cost of the materials used is just under $700, and of the project, roughly $7,000. There's a breakdown of the timeline. As you can see, we spent roughly 300 hours working on the design of our project. Now Ryan's going to speak about the prototype.
I'd like to start off. This is our first prototype that we rapid prototype. This is on a 2-to-1 scale. This is to verify fit and form of the teeth and how the pawl interacts with that. This is our second prototype. It's a 1-to-1 scale, and this better enables us to verify the fit and form. And we made a few modifications to the design to better facilitate the manufacturing process. So we converted some of the curves into straight lines so that we can do that better on the equipment available. So in order to verify our design, we use software simulation. We created the design in SolidWorks and also set up the simulation in the same platform. So instead of doing a quantitative analysis, we use the simulation as a comparison. So we set it up with a standard load of 1,000 newtons to be applied to the teeth of the weakest part in the whole system. And we used similar fixed geometry on the parts. And we did convergent analysis to ensure an accurate analysis. This is the original pawl, and we have a resultant safety factor of 0.15. This means we can have a theoretical load of 1,500 newtons to be applied to the teeth before failure. The pink arrows indicate the force, and green indicate the fixed geometry. In our design, we have an increased safety factor to 0.19. So this is an increase in the allowable forces to be applied to the teeth. And we also simulated the hub just to make sure that the teeth on the hub would be okay as well. It's significantly higher at 3,300 newtons. And you can see a top view of the hub and pawl interaction. Based off of the teeth, you can allow the hub to advance in a counterclockwise motion, but a clockwise motion will lock it, and this is what advances the socket. And this is a full overview of the head assembly. This is the manufacturing process that we used. On the left is a standard knee mill, and on the right is a standard engine lathe. Both are manual. Keep in mind that this is all done by hand, no CNC equipment used. There's a few pictures during the manufacturing process of the parts. This was a very long and drawn out process. Took quite a bit of effort on our part to make this happen. We have lathe work and some of the work on the mill. And we use a variety of different end mills and drill bits and lathe cutters to perform their tasks. And we also had an index head, and this allowed us to have precise angular rotation for the hub and round components. Once the parts were manufactured, we needed to heat treat them to make sure that they were strong enough during impact and during wear. And on the first section here, we have a preheat, and we bring the parts up to 1,400 degrees. We let it sit there for about 15 to 30 minutes, and this equalizes the temperature within. And we bring it up to 1,750 to begin the austenitizing process. Now, during this time, the crystal structure within the material rearranges to a more dense pack, thus resulting in a harder material. This is what allows us to apply impact and force to our teeth. And then we bring it out of the oven and right back down to room temperature within a matter of 30 minutes or so, and immediately back into the oven at 450 degrees. This is important to reduce any thermal shock stresses that were induced by bringing it from 1,750 to 0 in a very short time. This also restores some of the malleability of the steel, and produces the final product. And here's some images. This is the oven on the left that we use. This is an open atmosphere oven, no vacuum or no salt bath. These are parts just as we were about to pull them out of the oven. They're very, very hot. I'm going to pass it off to Milton to describe some of the testing procedures that we did on our components.
Thank you, Ryan. So after the manufacturing was done, we start testing, right? Our main goals were to increase RPM and increase torque. So we had to test for that. Also, we test for hardness because since we're increasing the load being applied on our product, we want to make sure the product is not going to break. So the first test that we did was raw hole hardness test. Why did we choose this test? Well, first of all, it's accurate, it's simple to do, and it's commonly used. How does it work? Well, it works by indentation depth. So a load is applied into the surface of our material, and this load causes a little displacement on the surface. And by measuring the displacement, we get our final value for our hardness. Also keep in mind here that we're trying to create a balance between the hardness and the toughness of the material. So we did the material in our steel 2 times, one before heat treating and another time after heat treating. Those are the 2 values that we got for our tests. And the scale that is commonly used for hard steel is the C scale. So what does this 50 mean? So for this kind of steel in this scale, 52 to 58 is about the maximum hardness you're going to get. So we're pretty close to that. After that, we did a torque test. So with the torque test, we had a steel plate, and we welded a bolt into it. And with both a standard ratchet and our ratchet for comparison, we fastened a nut into the bolt until it would stop. At that point, we would get a torque wrench, and by applying load little by little on the torque wrench, increasing the torque little by little, we would try to fasten the nut even further. When that happened, we took note of the number. And as you can see, our part exceeds the standard ratchet by a little bit. And also, this is important, since we're applying more loads, the simulations that Ryan presented before, it's important to note that our design can take a safer safety factor than the standard design. So after that, we did the RPM test. With the RPM test, we used a tachometer and a reflective tape. The reflective tape on the socket head, and that gave us our value for our RPM. The RPM from our tool is about more than twice as much as the RPM for the normal tool. And now I'm proud to present to you guys our final design. So this is our final design here. The handle is where the turbine is. We didn't touch that area. So this is where we changed it, the head. And you can see our final design with the sockets, the standard sockets that we can use right next to it. This is a closer look on the part that we actually manufacture and design ourselves. And this is a side view where you can see the pass-through mechanism that we incorporate into the ratchet. So as a summary, again, our goals were to increase safety, increase RPM, and increase torque. So this is a summary table with both RPM and torque that I just mentioned, just to give a quick an idea again that we actually achieved those goals. But some people might say, okay, there's a catch there because we spent $700 manufacturing this, and you can get a standard tool for about $100 in a place nearby. So why is that? Why do we spend $700? Well, we customized our entire design. That makes it expensive. We didn't have enough. We were limited in the things that we could do, especially in manufacturing. We ordered only a little bit of material, so the price per part of the material is expensive, and so is shipping. So where are we going to go from here? What are we planning to do now? Since this design doesn't exist, it's a unique design that we incorporated, we want to make a patent for our design. This patent would fit into the utility category, and all the costs associated with it should come out to about $5,000 just to patent our design. So for development, since we're limited on our manufacturing, maybe a CNC would make the tool more accurate and a superior tool. And another things that we could improve that we didn't touch in this project are the impact mechanism and the air turbine. Things we have learned, the interactions among the team members is essential for the success of this project, and this has to be made in an ethical way, because this is the only way that we can make things efficient. Also, during our design and manufacturing part, we learned a lot about redesigning for easing manufacturing, like we showed with our prototypes. We learned more about the manufacturing processes and also the importance of engineering drawings for the manufacturing part.
So there's a few people we'd like to recognize and give thank you to. First of all, our advisor, Dr. Basil, for always having his door open, always being accessible to us, giving us advice and constructive criticism when necessary. Thanks a lot, Dr. Basil.
I'd like to thank Mr. Rick Zigarelli, director at the EMC here at FIU. He was always available to help us out with the manufacturing process. He gave us a lot of tips and advice while we were machining, and he was always available when we wanted to come right before he had a long day of work, ready to go home. So I want to thank you for that. You're welcome. I'd also like to thank you, Dennis Moreno, and the engineering and manufacturing team at Skeletal Dynamics for graciously allowing us to use their heat treating equipment and facilities. Thank you again for that.
And our friend Ozzy Fernandez for helping us welding our final piece. Thank you for that. And now I want to open the floor for you guys for any questions.
Who's your potential customer? In other words, what industries are you really looking at with this tool?
This tool is based off of a consumer home mechanic tool. However, it is applicable to mechanics for automotive, aerospace industry, assembly facilities, pretty much anything.
Because of the features that it has, it should be applied to anywhere you can use a ratchet.
You know, most mechanic shops have an air supply. The facility I work at has an air supply, so it's very common, very applicable. A lot of home mechanics have air compressors at home, so with the adapters you can set it up with any system in the world.
I used to work as a mechanic. I could definitely use that a bunch of times. That's
Yeah.
a great idea.
The low profile head allows you to access small areas as opposed to having the long deep sockets.
Yeah. What's your biggest, this is my last question. What do you think, you personally, what was the biggest challenge doing this project?
Well, for me, I'm sure for all of us, was definitely the labor, the man hours that it took to actually manufacture it. We're lucky that Ryan had a good amount of experience using these tools. Milton and I were a little more amateur when it came to using them, but we both learned a lot, as did Ryan, I'm sure. And it was just a lot of labor, just very labor intensive, the whole process, because we ordered the steel rods, rectangular rods of steel, literally made everything from scratch.
Yeah, also some stuff we couldn't do it ourselves, such as heat treating and welding, so also we had to outsource some stuff.
Definitely manufacturing. We had to come up with a lot of clever solutions to do the tooth profile of the hub. The pawl was kind of free-handed. So it was really stressful to create these components, but in the end it came out all right.
It didn't just come out the first time, so
Yeah.
we had to manufacture it.
Trial and error.
Went through a few drill bits as well.
It gave you, it gave you some concept of tolerancing blueprints, I'm sure. Because we see a lot of tolerances that are nuts, and almost sometimes impossible. And you can tell it's an engineer that never turned a lathe on or never ran a mill. Because once you do that, you go, oh boy, I'm going to put plus or minus 5,000s, and plus or minus 1,000, just a whole mess. The second comment is, you know, when you go to the manufacturer, this is the kind of stuff that ends up being made out of powdered metal. And powdered metal tool steel, once it's sintered and heat treated, is very, very tough. As a matter of fact, our gear cutting tools, a lot of them are now made out of powdered metal, and then ground to the finished sizes, but in powdered metal, you can take them right to the finish, and those would be 50 cents a piece to make those.
Okay, we'll definitely take
It's
that
it's
into
amazing.
consideration.
The tooling will be $50,000, but the parts will be very, very cheap to do when you get it down to that final science. I noticed you welded on there. Did you do any after the welding testing of the welds, like a
No.
mag particle inspection or anything like that?
No, that was more or less non-structural. That was for the head. That component was just designed to hold the hub, and it had a very large surface area, so we weren't concerned with that.
No, not, the load applied to it is not too strong, so we weren't too worried about it.
Did you weld it after the heat treat?
No.
That was welded
components-
before.
Those components were actually not heat treated. The threads were pre-manufactured. We didn't want to heat treat those and deform them for fear of not being able to assemble the final tool. So since it was a less impact, it didn't have much impact. There was a very large surface area on the wear components. We neglected heat treating on that one.
It's my turn. You made the statement of reducing air consumption would help reduce the cost of running the mechanic's shop or manufacturing facility. How does this particular device execute that?
Comparing left and right with the standard air ratchet, your rotation speeds are 150 RPM, and that advances a thread at 150 revolutions per minute. So it takes X amount of time to fasten a bolt or a nut. With this tool, the rotations are increased by almost double, and it'll advance the nut or bolt that much faster. So the air consumption going into the turbine is the same for both turbines, but the time that it's spent running will cut that air volume by half.
The reason I asked the question is the line that you're running out of is the same line.
Yes.
The compressor that you're running off of has to keep that line solid all the time. So is it really going to save you any money?
Absolutely.
It's not that we're gonna use less air per unit time. Is that instead of having a longer time using the tool, we're gonna have less time for using the tool. So this amount of time that we're using less is gonna save the amount of energy.
Okay, and then the second part of my question is tied to 400 RPM. Is that, have you done all of the failure modes, effects analysis, and safety analysis to prove that I'm not going to hurt myself with this 400 RPM?
By designing, yes. Using the previous design as a safety factor, that tool obviously has a set safety factor.
Yeah, I can't make that assumption. You've got to make the assumption that your design, you got to prove to me that your design's safe. Not that based on their design, your design is safe.
Correct.
Okay. In your report, you said that you had FOSs of 0.15 for the original hull. Is that adequate, a 50% safety factor?
That was, again, I mentioned for comparison rather than for a quantitative analysis. So by comparing left and right, I applied 10,000 newtons, which is astronomically huge for these small components. And at 10,000 newtons, they are going to fail. By determining the safety factor, we establish the point where they fail at. And if we note an increase in that safety factor, our design is stronger. So from original to our design, that strength increases.
Okay. My last question. With intense spikes in force, which some of these components are going to endure shock, did you do any work to understand what the impact of shock would be on this device?
No, we did not. That's a very complex subject, of course. We are relying on the physical design of those components. The original design did have that same impact mechanism acting on it. So by establishing those benchmarks and making it stronger, we are then assuming that the final design, our final design, is stronger and can withstand those forces.
Okay, thank you.
I got one question. What safety provisions do you have in this device that would guard against shearing fasteners?
Well, actually, the through-hole feature, we're hoping will improve that safety aspect, because using long sockets is more prone to shearing than it is if you have the actual socket within the top of the tool, inside of the tool.
I guess a related question is regarding standards. I think that you've made good reference to the standards that govern your work. What about the standards that limits the performance of all those additional devices that you've incorporated?
You talk about standards, for example, that would limit the original tool.
Exactly.
Is there a standard for that? I don't think there is.
There are ISO standards for the performance of pneumatic tools. They're available for purchase, and we attempted to get that information, but it's very expensive. So in order to bypass that, we neglected that.
But if you're going to be marketing this, you're going to get a patent, you're going to market this, you may want to deal with that.
Exactly. As soon as we get an investor, we're going to definitely take care of it.
Once they find an investor, yes. Thank you very much.
All right.